Welcome back, and now we are going to finally look at some determinant methods, or just kind of review some. In the last video we saw that if we have a 3 by 3 matrix, we can compute the determinant by doing the first column dotted with the cross product of the second and third columns. So that's fine, but in order to do a determinant you have to compute a cross product, which might not be super time efficient or time effective. So what other methods exist? You might remember that cofactors, yep, we're going to get to cofactors, but before we get there, I want to give you one other method that you may not necessarily remember. I call it basket weave method. Formally, it's called Sarris's rule. So you can go ahead and Google that if you want. But the idea of basket weave is that you end up rewriting the first two columns after the last column, so 3, 2, 1, 1, 7, 0, and then you take the diagonal products going from upper left to lower right and add those up, and then you take, so let's just do that. So we take this one, and this one, and so those diagonal products end up being 21 plus 1 and then plus 0. Okay, and then you subtract the anti-diagonals, or the diagonals going backwards. So that would be this one, and that one. So then we end up with subtracting 2, subtract 0, and subtract 28. And so then I would say if this is, determinant of A is equal to, so this is equal to, and then equals to, okay, so 22 minus 2 is 20, and then minus 28, is minus 8. Okay? So, just a little introduction to basket weave. Now, I want you to try this one. For which one is it invertible? So we just need to make sure that the determinant is not 0. So try that out. You're going to look at the determinant of k01, 0, k, 1, 0, 0. Okay, and if you solve this, you'll see something interesting. So try it out now. All right, and if you solve it, the determinant ends up being minus k. So then, and we know that this cannot be 0. So then we would just say that the answer here would be all k in R not 0. Okay? So the only bad thing about basket weave is that it doesn't generalize to n by n for n greater than 3. It works for 3 and it works for 2, but not anything higher. Okay, so the third method that we're going to look at is cofactor expansion. Now this is the case that works in pretty much in all other cases, and so here's kind of the process. You're going to pick a row or column to expand along. Really, the row that you want to pick is the one with the most zeros to make the calculation easier. And then the values in the row or column are multiplied with this I to the, or -1 to the I plus j, which is the row and column number with each term, and then you multiply each coefficient, which is that -1, and then the factor by the corresponding minor matrix. So, for example, if we expand along the first row, we'd have A11 and then times -1 to the 1 plus 1, and then the minor matrix would eliminate the first row and first column, so we'd be looking at the determinant of A22, A23, A32, A33. Okay, and then if I, well, there's an A there, and there's an A there. Okay, and then, so that's the first one. I need to continue, so then I would add to it A12 times -1 to the 1 plus 2, and then the minor matrix associated to A12, again, eliminate row and eliminate column, A21, A31, A23, A33. Okay, and then the last one I need to include is A13 times negative 1 to the 1 plus 3, and then the minor matrix would be A21, A21, A31, A22, A23, and then multiply all that out. So just as a practice, I want you to write out what it would be expanding along the second column. So pause video, try that out. And you can see my answer here. If there are any typos, I apologize, but you get the idea. Just double check your work with my work. Okay, and then lastly, to wrap this up, an example. It is a 4x4. Now, we didn't do a 4x4 in the example up here. Theoretically, if you end up with a matrix here, like the minor matrix is something larger than a 2x2, you would have to continue to do the cofactor expansion. So it does get to be a little lengthy. But again, maybe you can do this efficiently. Okay, so I want you to pause the video, try computing this determinant, be careful in your choice of row and column. Okay, if you were careful, you might have noticed that the second row has 3 zeros. Okay, pick as many zeros as you can just to make your life easy. So what I'm going to do is say that this is going to be equal to, again, the cofactor expansion, you can pick any row or column, so I'm going to say this is 4 times and then negative 1, and this is in the second row and third column, and then I'm going to also eliminate the row and column corresponding to this. So then I have to take the minor matrix 3, 0, 0, 2, 4, 3, 1, 1, 1, and this one again you can do cofactors for this, and I will, just to illustrate that. For that one, I'm going to use the first row, so then I would multiply by 3 to the, or times negative 1 to the 1 plus 1, and then times the minor, 4, 3, 1, 1, and so then I get, let's see, this is going to be negative 4, and then that'll be times 3, and then this is going to be times 4 minus 3, so then at the end I get minus 12. Okay, so another way to compute determinants, again, we have, if a 3x3, we have the cross product and dot product definitions, Baskerville and Sarris's rule for 2x2s and 3x3s, and then more generally we have this cofactor method. Okay, cofactor expansion. In the next video, we'll see yet another method.